Hi everyone. Today I will talk about how to use graph technology to do the anti-money laundering and fraud detection on Iceberg data. First, let me introduce myself. I'm the CEO and the co-founder of PuppyGraph. Before that, I worked at TigerGraph and the Google F1 team. Google F1 is the unified SQL query engine inside Google, can query all the data as it is without moving it. And one SQL statement can query multiple data sources. The story is that when I was at TigerGraph, talked with a lot of big banks and big insurance company, and only the largest one like Bank of America and JP Morgan Chase and United Health can afford it, since they pay us millions of dollars per year. And non-tech company is using TigerGraph at that time. I think there must be something wrong. So I joined Google because it was a safe choice. And after that, we realized people want to do OLAP. They want to query the data as it is rather than have another data stack, which is hard to scale. And for example, a lot of data sets are nature to be graph. For example, if you people transfer money to some other people, and people have cars and IP address. In this case, it's nature to modeling as a graph, but usually the data is already in table format. And the similar thing happened in cybersecurity, observability, social network, and a different area. There are different ways to solve this problem. One is that they just batch loading the data from data warehouse or data lake to a graph database. There is another way that just use SQL to implement the graph. But both of them have a very serious issue. One is that usually the data warehouse and data lake data is much bigger than graph database can handle. Like no one use Postgres to do heavy data analytic workload in current days, but people have to use graph database to do the data analytic. And for the SQL one, when the query is complicated and real in graph, SQL is very hard to express it. Sometimes even people can compile the graph into SQL, but the other guy cannot understand by reading the SQL script. It's usually hundreds of lines and with a lot of joins. So that's why we come up with PuppyGraph. We just want to query the data as it is as a graph. So you don't need to move the data, and we support a different data source. But the Iceberg is most is our favorite data source. As I mentioned, we created this company because of Iceberg. Since the Iceberg team left Netflix to create a company called Tabular, and we immediately worked with them. And because the cost is so cheap, and of course thanks to the S3 team, the performance seems every year is 3 times faster than before. So it's achieved the low cost and high performance at the same time. So by leveraging that, we can do sub-second graph query on petabytes of data. Here is a common practice. Usually there will be streaming data, maybe from Kafka, Redpanda, or Stream Native. They are our partners. And recently they both natively support Iceberg. It will streamly have the write ahead log directly go to Iceberg, make the streaming cost much lower than before. In this case, we can directly query the stream and also the existing data in Iceberg together. In this case, this is especially useful for the anti-fraud and anti-money laundering use case. It's because that the data is changing, but it have for the anti-fraud case, it don't have to be transactional with ACID. We just catch the latest updates and find who is the frauder or who is do the money laundering. Let me have a real example. in this table, in this case, we have several tables like users, profile, and also cars. And for cars, each cars have an owner, which means it will have a column like card A have owner like Weimo, and and maybe card B also have owner Weimo. So the owner is a column of cars table, and also it have devices and IP addresses. And we first have some labeled fraud user, and this is a query to show all of them. And this is an ugly picture. There is no useful information. The second step is that we want to establish some relations between the user. Here we take one example, like if two users transfer money before, and at the same time they share the same credit card, usually they belong to a same fraud group, and we want to have a relation, build a relation with all of them. And laterly, we can run some algorithm like WCC, which is a weak connected component, and then different group will different user will group together. Then we can use the Python client can consume the result, like who is the frauder. Here we see that when one of the group user is labeled as a frauder, and the others have transfer, we can see how they transfer money and how they share the different credit cards with them. So it's given you an explanation why this user is a frauder. Yeah, this is the main case, main content of the talk. And any questions? Yeah. Oh, thank you. Thank you. Please. Yeah, please. Yeah.
Static.
This is a good.
And another question I have is also, I worked in the graphs a lot, and I have seen, for example, what happened in IPs, not very reliable sources, and then to I mean, I worked with Tiger Graph in the past, too.
Yeah.
Kind of tend to create super clusters. How do you deal with kind of, I guess, super clusters use cases too?
Cool. Yeah, so what we are doing is that first, we only have a mapping from the graph schema to tables. In this case, even the data is updating, at the same time, the graph is logically updating. So we don't have a physical graph. We just physically, there are still tables. So when there are new coming ones, there are new records coming in, because we are lazy fetch, so the new results will reflect in the query. Since when, for example, when some people do the new transaction, and the query after you, and then you run the query again, the new result will have the new transaction. And this is also a benefit than graph database. Since for graph database, when you redesign your schema, you need to reload all the data. But now you just change the mapping. When you do the change of graph schema, you just change the mapping from graph schema to your data source. And at the same time, we can catch the latest updates of your ground truth data. You don't have a two data source sync between each other. Did it answer your question?
I guess.
Oh, cool. Thank you. Okay.
Hey, so I've got a question around your performance.
Yeah.
And how are you able to do this, specifically with key value lookups, for example, looking up by, say, the card IDs, especially if they're stored in, say, different Iceberg tables as the user. Yeah. How are you able to get this kind of performance?
Oh, this is an interesting idea. Since the first time I show, it's kind of hard to be true that most of the graph query will be faster than graph database. Since when I show this to Iceberg team, they also feel a surprise. Since when you have multiple query, so multiple hops of query, then the problem will be it's more like an analytic query rather than single record lookup. In this case, column-based will be much faster than row-based. But because the graph database have to be high QPS of transactional updates, it have to be row-based. So when you have multi-hops, you need to load a lot of unnecessary attributes into memory, and it's very easy to out of memory, and the performance is slow. But for us, because we can handle more nodes and edge at the same time, and also leverage the SIMD technology, vector evaluation, and multi-thread parallel computation, so it will be faster. But of course, if you just look up 1 or 2 hop, we won't have any advantage. But this is also a dilemma for graph database. If a user only use 1 or 2 hops, PostgreSQL works very well, and this is very hard for graph database to get in the market. But at the same time, most graph database cannot handle multiple hops, so it's a kind of dilemma for the graph database. So we only focus on the complex query, which cannot be achieved by SQL database like Postgres. Yeah. Yeah, sure.
Thanks. So are you creating a cached layer or say a graph DB representation of the underlying data in Iceberg tables? And are you storing that separately?
We have different option. You can choose whether you want to have cache or not. And also you can customize your cache strategy. Like only last week data, you could want to cache it, and for historical data, it will be a cache miss. And but only for sub-second or even faster query, you need a cache. Because if you just want to have about 1 second performance or single digits performance, you can just have a bigger cluster scale out. Because we are a cluster distributed engine, so one query can be handled by numbers of machines. More machine, better performance. So even without cache, you can speed up by have more machine and to have the good performance. Yeah. Any other question?
So we'll take one more question.
Yeah, a quick question.
Yeah.
Thanks for the presentation. Very impressive. Good stuff. One quick question. You mentioned the one feature pipe graph is implement is can join the lifetime both persistent data, which is already in the storage, saved, and capture stream come in.
Yeah.
That's pretty neat. Question is, how can you enforce integrity for streaming data? For example, you see example, you have a card transaction. How can you know that's account, that's transaction actually associated account you're looking at?
Okay. Since this is, we won't want to take the credit because it is most implemented by the streaming company like Confluent, Redpanda, and Stream Native. Like Stream Native called Author, and Confluent called Tableflow. And
Okay, so you rely on the upstream to make the data in card. Good.
Yeah. Thanks to the Iceberg community, the most feature we don't need to implement by ourselves. We can just leverage the other vendor and then make this happen. Yeah.
Makes sense. Thank you.
Thank you.
Okay. Thank you, Weimo.
Cool. Thank you.